Okay, so what we're going to do now is talk about the demonstration we're going to do, and I'll flip the lens here in a second. But we have 1, 2, 3, 4, 5, 6 different treatments, and this sheet or one very similar to it is in your Blackboard. It's one of the things that I posted. And so what we're going to do, remember last time or the time before we started talking about flocculation, swelling, and dispersion. Well, we're going to watch and observe this in action today. So that's what we're going to do. So if you have this sheet, keep it handy. I will refer to it quite often, and we will have the demonstration will last for a little while. Oftentimes I can get it done in 50 minutes, but I have to stop talking and start moving. So I'm going to stop talking here and start moving. I do have to check something real quick. It's one of those things where you don't want to get through halfway and then realize that you didn't hit record. So, okay. Ta-da! There's our little friend. And I think that's everything that I need up here. Okay, well, welcome to the demonstration. Welcome to the demonstration, the final demonstration that we have for the semester. And is it cold in here? It feels cold in here. I know what it is. I don't have my hat. I don't have a hat. So there we go. There's my hat. Okay, so I got this hat at in the uplands in Thailand. It was among community up in the hills, and I'm sure I paid way too much for it, but so be it. So what we have in our treatments, and I got to get these started so they get moving. So in the first one, the orange, we have a soil that is sodic. It has a high SAR, a low electrical conductivity. So when I say high SAR, it's about 13, 14. And it has a low electrical conductivity, meaning it has about 1 or 2 EC 1-to-1. So remember that it's kind of at that ratio cusp that we're talking about, where you want it to be less than 5x. So that's that one. And we're going to wash this one with deionized water. Low electrical conductivity water. The second one is the same soil, but now we're going to add calcium chloride, half molar calcium chloride. And the reason is we're going to add electrical conductivity, but we're also going to add that calcium, which is a flocculant. The purple one is high SAR, low EC, same soil, but this one we're adding 10 tons of flue gas gypsum. And flue gas gypsum is a byproduct from the coal combustion industry. In North Dakota, we have one plant that produces this, and it's the Leland Olds plant. So back in 1990, through the Clean Air Act, power plants were required to strip the sulfur out. And so what they do is they use a slurry of calcium carbonate, and through forced wet oxidation, they're able to precipitate out the sulfur, the sulfate, and combine it with calcium to produce calcium sulfate. So we'll talk about this in a little bit later. But most of the time, it's fairly powdery. It's hard for you to see, I realize, but it's pretty wet. Sometimes it's like 30% water content. So you do travel, you do haul a bit of water when you pick this up. Okay, so the second one is high SAR, the blue one. High SAR, low EC, 10 tons of commercial gypsum. So these are pelletized, and then we're going to wash it with DI water. So these are your typical pellets. You can hear it. Okay, so you can. These are pelletized and very common. You know, most of our live bottom spreaders that throw urea also can throw the pelletized gypsum, and we'll talk about that in a little bit. The solubilities are the same. The difference is in a powder form, for the amount that we add, we have millions of little particles that we add. And for the pelletized, you might add 20 pellets. Okay, so think about that from a surface area to volume ratio, right? You have a lot more surface area with a clay soil than you do with a silt soil and a sand soil. In the same vein, if you have a powder, you have a lot more surface area per mass than you do with pellets. So it's the same concept. Solubilities are the same, but you have more of this to spread around in the soil. And so the yellow one, Old Yeller, this is sugar beet spent lime. So this can come out, our sugar beet processing plants in the valley and in Sydney, and most plants that process sugar, they use calcium carbonate in the clarifiers to precipitate out some of the colors, the proteins that are in the stream. Therefore, when it gets precipitated out, it's a byproduct, which is oftentimes called spent lime. It has about a 70% calcium carbonate equivalent compared to pure lime. And one of the things that it's used for, because it does have about 1% P2O5, so it can be a phosphorus source. But if you remember from our previous lectures on salts and solubilities, the solubility of this is about 35 times less than the gypsum. So remember, this was about the mass of a penny in a liter of water. Well, this is 35 times less at least. So the reactivity of that is going to be less than the gypsum. But it is still a source of calcium. And we do have growers that are managing their sodic soils and asking these questions about, can we use sugar beet spent lime? It's not very expensive, but it's not very reactive either, so it's a trade-off. So the last one, the red one, is a non-sodic sandy soil that has low electrical conductivity. And what we're going to do is this is a soil from oaks. So it's about 70% sand, and so it's very, very coarse textured soil. But what we're going to do is we're going to make this into a sodic soil. We're going to make this behave just like the high SAR, low EC, the orange one. But it's going to take a little bit of a manipulation on our part. So what we're going to do is we're going to start adding water to the first 1, 2, 3, 4, 5, and then we're going to add sodium chloride to that one. Or excuse me, we're adding calcium chloride to the green one, sodium chloride to the red one, and the rest of them we're going to add deionized water to. So. You can have a high electrical conductivity and water will move through just fine. So water's already moving through on the coarse textured one and on the calcium chloride one. Water's already moving through. So you'll be able to watch now the change in height of those cups. So. Okay, so we're going to let that stew and fester, and we'll monitor that. But you can already see the green one's already moving down, and then the red one is starting to move down as well. The reason is, of course, is that you have high electrical conductivity with both of those, which is basically controlling the diffuse double layer, the flocculation, so your water's moving through just fine, and the fact that you have a exceptionally coarse textured soil on the red one. So. Okay, so we'll go back and forth to that as we move. Okay, so let's talk about one of the things that we've been talking about is sources of calcium. That if we add calcium, we add a flocculant, we can start to get water to move through. So let's talk a little bit about sources of calcium. So gypsum, this is the main one. Again, if you remember, this is calcium sulfate and it's got 2 hydrations of water to it. And this is, you have 2 different sources of this. You have mined, and then you have synthetic. And the synthetic, even though it's still a crystal, it's still a salt, if you will, it is made through a synthetic process or an industrial process. So these, from the mined ones, these are most likely pelletized. Most likely pelletized. And the cost for these is about, and it depends. I mean, it's like shipping costs and so on and so forth, but it's about $200 per ton. Okay. So, and probably if you're bringing that into North Dakota, most of that is probably going to be due to the shipping. We'll add to that anyway. So the synthetic, as we talked about a little bit, this is a byproduct from coal combustion. Byproduct from coal combustion, usually cakey, but it's mostly in the powder form. It doesn't work well in live bottoms because it bridges pretty bad, and you don't need to be up in there beating on the sides of the trailer to get that, or the hopper to get that to move through. So now available is less than about $15 per ton. Okay, so the quality is really high. I mean, the quality is as good. The gypsum, mine gypsum, the quality is as good as the synthetic gypsum and vice versa. So, but you can see, right? I mean, this is awfully quite a bit less expensive, and both are very pure and are good sources of sulfur too. Okay, so we did some studies. We looked at flue gas gypsum and with fertility of canola, and we found that to be as equally or better than ammonium sulfate or the Tiger 90, which is the elemental sulfurs. So yeah, it can be a good source for. It's fairly inexpensive, and so it can be a good product for that. So the sources, if we continue on, so this is then be sugar beet spent lime. And that's the stuff that we have in our demo. Okay. It is shown to have lots of beneficial uses. I always forget the disease in sugar beets but adding the sugar beet spent lime tends to decrease the incidence of that disease. It's a root disease. But it has very low solubility. And so it's not ideal for sodic soils. Not ideal for sodic soils. It has organic compounds in it. And they're very degradable. Put a lot of varies in here. Very degradable. And can improve microbial respiration. We've done study after study after study. Every time when you had this sugar beet spent lime, microbial respiration goes up. So it can be a very good microbial additive, if you will, because there are microbes in the process and blah blah blah, and you add those to soil, and the fact that you have all these very degradable organics. When you add to the soil, it's kind of like adding a little bit of sugar, and therefore the microbes do like sugar, not unlike myself. So calcium nitrate. We will never use this in production ag, but it does have a very, very high solubility. Has a very high solubility. And it can be used, or often used in reclamation of brine spills. So what would happen then is they would use the calcium nitrate, they would have a tile drainage system, and then they would move that calcium nitrate down through the soil, collect it, and then discard it. They wouldn't add a whole bunch of calcium nitrate and then just let it sit there, for the one reason, of course, you don't want to add all that nitrate. And in brine, as I stated before, most of it is in a chloride form, and just moving the chloride to a lower place into the groundwater is not allowed. So you would actually add this salt, move it through, you would collect the nitrate and the chloride together and dispose of it accordingly. So that's our sources of calcium. And those are, pretty much, unless there's something that's proprietary, there's not much else in the way of calcium sources. So I need to go back over to our demo here. Let's go back over here and see what happened. Well, let's look at this one right now. So this again is the non-sodic soil, very coarse textured. We added 1 molar 1 molar sodium chloride to that. You can see that it has this kind of funky color to it. Anybody want to take a guess at what that is? Going once, going twice. Sold. Good question. Good answer. But it's organic matter. It's dissolved organic matter. It's being moved through that soil. Probably a little bit of chelation, a little bit of ion pairing, and it's moving that down through. So what I need to do is put this in this bucket so I don't. Okay. And the other one that we're looking at now is the green one, and that is remember that was the calcium chloride, and the next one was the flue gas gypsum. So just because I'm here, I'm gonna dump the green one away too. Okay, I'm gonna let the other one sit because that one will take a little bit longer. So, okay, come back here, take a little gander. So we have in the orange one, this was our sodic soil. We added water. Not a drop of water has come out, nil. In the calcium chloride one, we start to see some water moving through because of the high electrical conductivity, because of the chloride. Here, this is the powder flue gas gypsum. Hey-oh, we're getting some water move through here. Blah, look at there. This is the pelletized gypsum. Remember, we had millions of little particles in the powder, and we had probably 20 pellets total. So unless those pellets are all lined up in a column, we probably won't see much water movement. This one is the spent lime. As you can see, we don't have, well, you may not be able to see, but we don't have any water that's moved through either one of those. And lastly, we have our coarse textured. So we already moved through 1 volume of water. We're gonna dump that out, and now we're gonna add water to this one. We've put sodium on the exchange sites. We still have a high electrical conductivity because there's still water in there. That's part of our, remember, that's part of our field capacity water. This is basically at field capacity. And so now we're going to reduce the electrical conductivity, but leave sodium on those exchange sites. So let's get our rainmaker out again and add a little bit of dihydrous oxide. Which is safe to drink. I don't have any to give you at this point, but chug-a-lug, chug-a-lug. All right. Bloop. Okay, so let's go back to So here we have our high SAR, low EC. Water has not moved through. Here we have our calcium chloride added to that same soil, moving through just fine. Here we have our flue gas desulfurization gypsum with deionized water. Looks pretty good. It's moving pretty good. Now, don't expect this to happen in your field at home. It takes a while for these reactions to occur, but we're sort of speeding it up by concentrating it. This is the pelletized gypsum. No water has moved through at all. This is the spent lime. No water has moved through at all. But look at here. Remember how fast the first one went? What do you think all this stuff is? You can see it behind my shirt, I guess, a little bit better. That is dispersed organic matter. And so what this Sodic soil is doing is creating dispersion on the inside, in the pores, on those clay particles. The organic matter is being dispersed out, and that's the black stuff that you see coming out the bottom. Notice how slow this water is now moving. You know, the first one just basically went through without any issues. Now we've created a Sodic soil. So this can happen if you use irrigation water that doesn't have good quality, if it has a low electrical conductivity and a lot of sodium in it. This demonstration here. Okay, so what this will happen, and I'll show you next time, is this will flocculate. It started, but you won't be able to see it. And then what will end up happening is it'll be clear liquid at the top, and then this black stuff will be on, this organic matter will have settled to the bottom. So I'm going to set this over here, and when we do our last video where we go over the exam, I'll show you that during that time. Okay, recap. So we have a high SAR water, low electrical conductivity. This water has not moved. This is exactly like the pictures I showed where the water just sits in the field and does not drain. Okay? We can leave this here, literally, figuratively, however you want to think about it, for years. If we stop the evaporation from occurring, we can come back here for this class next year. Most of you, I think all of you, are going to be moving on. This water will not have moved. Okay, this is basically what happens when the soil is swollen or dispersed internally. Water will not move. However, if you have a high electrical conductivity and add calcium, this is what's going to happen. You're going to end up with water moving through just fine. Now, we can't. This is the essence of reclamation or amelioration. This is what we want to happen. Oftentimes, we can't add even that much water in a field situation because of the fact we don't have that much water, and we don't hardly get that much rainfall when a lot of it is evaporating as we apply it. Okay, so this is the flue gas gypsum with the powder. It's going to move through pretty good. By the end of the day, it's probably going to be moved through. Then you're going to have basically calcium on those exchange sites and sodium being off those exchange sites. This one is the commercial gypsum, the pelletized gypsum. Okay, the solubility is the same. From the powder to the pellet, the solubility is the same. It's just the surface area to volume ratio that makes the difference. This one's the spent lime, again using deionized water. You know, there's some. You know, it's going to start moving over time, but it's certainly not the best option. If it's the only thing you have, it's the only thing you can get. You know, it's not going to hurt anything, especially if you're interested in it from a phosphorus standpoint as well. And remember, we moved the soil. We moved water through sodium chloride through this soil. We put sodium on the exchange sites. We've now reduced the electrical conductivity, and this water has basically stopped moving. So we created a Sodic soil. We dispersed the organic matter that was in that soil. That's the black stuff that we see there. I will flocculate that, and by the time we meet again, that should have settled. And it does take some time. It's not instantaneous. Okay.